Okay, so in the last lecture, we have spoken about metric spaces, and how to complete a metric space. Okay, and we have argued, we have discussed why to have a complete metric space is important. Okay, in which sense completeness of a metric space is essential for every mathematical and mechanical application of our theory. Now, we must try to approach the problem of the equilibrium of a beam, of Euler-Bernoulli beam. I decided to use an approach which is a little bit different than the usual one, which I prefer usually. In general, I prefer to have the most general theory, and then I particularize the most general theory to some specific cases. Now, maybe it is better that we do the other way around. So we start with some particular examples, and in future lectures we will see the most general theory. The reason is that I want to show you some parts of Euler-Bernoulli theory in which you need a very unusual or unsuspected metric. So, we have the space of configuration for a beam. Okay? So, let us just, for starting, let us assume to have a beam which is clamped. Okay? We have already said that for us a beam is a set of sections which remain rigid. Okay? And you have the elastica, the elastically deformable curve, which is made of bicenters of this beam, which we are drawing, and which represent this curve represents the configuration of the mechanical object we are trying to describe mathematically. Okay? So, if I introduce the curvilinear abscissa S of the curve in the reference configuration, the actual state of the, here we have the real world object. So the state of the physical object is modeled by a configuration, which is a mathematical object. What is this configuration? Is the set of displacements of every section. So you have a function u, vectorial function u of s. If d1 is here and d2 is there, u of s is equal to u s of d times d2 plus ws d1. This is the displacement. Okay? The displacement is given by this function. So you have two scalar fields, transverse displacement and axial displacement, and these two scalar fields are describing the configuration of the system. Okay? And we said that this is an infinite dimensional vector space. Okay? You remember, we said that in the set of, for instance, just for starting our reasoning, these two scalar fields must be continuous. Why? Because elastical phenomena are not producing breaking of the beam. Okay, so the beam remains a unique body. In order to have this condition verified, the function us and the function ws must be continuous functions. Okay? The set of continuous functions C0 is a vector space. We said this several times, and the sequence of all polynomial of basis polynomials. So the set of polynomials like this, where n can be 0 and every natural number. This set of polynomial constitutes a set of linear independent vectors in C infinity. Okay? So we have an infinite dimensional vector space, which is the main difficulty in our discussion. Okay. Now we want to introduce a deformation energy for this beam. Why? Because we want to find the stable equilibrium configurations under certain external actions. The external world is acting on this body, and it is imposing a deformation to this point. For instance, let us consider a simple case. We can impose a displacement delta of this clamping device with the section which remains orthogonal, which remains parallel to the reference configuration in the actual configuration. So we have that the beam has to choose one equilibrium configuration having as boundary conditions the fact that here the rotation of the section is 0 and the displacement of the section is 0, and here the displacement of the section is vertical and the rotation of the section is 0. Okay? So our problem is to find this equilibrium configuration. Our general principle, as we said several times, the meta theory which we want to use for developing this theory, meta in Greek means beyond. So if you talk about a meta theory, a meta theory is a theory discussing about theories. Okay? So, the theory of beam is discussing about physical objects. Okay? The principle of minimum of energy is part of a theory which has as an object other theories. By the way, this for mathematicians should not be new. Okay? Why? Group theory is what? Is a theory which describes how to build algebraic structures. So the object of group theory is real numbers, complex numbers, vector spaces. So group theory deals with some properties which are in common with all these theories. Okay? So, at the end of the story, you should not be surprised that we need systematically a meta theory. However, the meta theory based on the principle of minimum energy is not teaching us how to build other mathematical theories. It is teaching us how to build a mathematical theory for describing physical phenomena. Okay? Don't believe that one can prove experimentally that the principle of minimum energy is valid. This is absolutely meaningless. Okay? In this aspect, there was a famous philosopher of science, Bertrand Russell, who gave a wonderful example of the situation. You know, many believe that you are very careful, so you build many beams, you see which is the shape in equilibrium of these beams, and then after a lot of experiments, you can decide beams place in the minimum of energy. This procedure is totally senseless. Okay? Bertrand Russell was very cleverly representing the situation with this small, meaningful story. You are a Turkey, who is a very good experimenter. Turkey. So he is following the rules of naive inductivism. Those who believe that observing many phenomena, they can obtain theories. We can call them naive inductivists. Okay? The Turkey observed that every day, 7 o'clock in the morning, the farmer was feeding him. He was very careful. So he observed that the farmer is feeding him Monday, Tuesday, Sunday, when it is raining, when the weather is good, if the farmer quarreled with his wife or not, if the children are in the house or not, and he makes a lot of observation. At the end, he claims there is a physical rule. I am fed every morning at 7 o'clock. And he formulates this in the day before Thanksgiving, when it is very well known that turkeys are killed for preparing the Thanksgiving party. You can observe 1 million times that the sun is rising every morning. You cannot formulate the law that the sun would rise forever. Now we have observed some stars becoming snowy. So, this theory has been falsified. So we cannot in any way prove that every reference, every equilibrium, stable equilibrium configuration is the minimum of an energy. This is a conjecture. What I can tell you is that up to now, every stable equilibrium has been associated with an energy, and this energy in that equilibrium configuration has a minimum. So this is a powerful tool for predicting phenomena. If this principle is universally valid, at the end of the story, it's not our business. We will apply it until it works. If we find a situation where it is not working, we will be obliged to change our meta theory. Okay? More details about this discussion you will find in the chapter I have distributed. Okay? And we will go back to this point several times, giving more and more examples. Okay, now you want to find the minimum of a functional. Okay, we call it functional. Why? Because it maps functions. These functions must be tentatively in C0. And to each function, giving you the shape of the beam, you associate one real number, the energy associated to that function. Of course, we are looking for functions having these boundary conditions. So we must find among all functions having zero value here, no displacement here, no rotation here, given displacement delta here, no rotation on the right end of your beam. Among all these functions, you must find the function or one or many, the functions, the set of functions, for which the energy has a minimum. Okay? So it is essential that you must learn how to find minima of a function. Okay? So what we do? We go back to what we have already learned in calculus, mathematical analysis, first year. So we go back to a function f of x, okay, and we have learned a technique, an analytical technique for finding minima. Now, let us discuss shortly the main ideas of this technique. First of all, I have a point x0 where my function has a minimum. Okay? By definition, this means that I have a small neighborhood of x0. I have a ball centered around x0 such that, so I can tell you that for every x such that distance of x from x0 is smaller than a given radius, we have that f of x is greater or equal to f of x0. This is the definition of local minimum. Of course, for this definition, you don't need continuity. You don't need anything. You need only the definition of the function f. Okay. Now we go back to our mathematical modeling of theory of beam. Okay, so let us discuss a little bit the meta theory we are trying to use for building the model Euler-Bernoulli beam. Do you think that if I deform a little bit more or less, if I change a little bit the deformation of my beam, the energy is changing a lot? So the idea is, I must have a definition of continuity which can be applied for the deformation energy. So I must tell you what happens if U is modified with a small delta U, a small variation of shape induced by a small variation of displacement. And when I have this small variation, the energy must vary a little bit. Of course, everything can be made rigorous in terms of mathematical definitions, and we will do it. So, are we happy with the extra property that the function is continuous? We are not. Why? Because we have learned that for a real function of real variable, the most efficient algorithm used for finding maxima and minima require the calculation of the derivative. We have proven, and we will now discuss a little bit this argument, we have proven that in a minimum or in a maximum of a function, valued function of real variable, the derivative of the function, if exists, has to be 0. You should not believe that every function has a derivative. There are functions which are continuous everywhere and nowhere differential. There is a function which is called the stir of the devil. This function is increasing, continuous, and has almost everywhere the derivative 0. There are terrible functions, very strange functions. Okay? However, in mathematical analysis, we study a class of functions. So think about Shakespeare. Our ideas are much smaller, have a range of complexity much smaller than reality outside. So we limit ourselves to study functions for which the derivative is existing. And for this class of functions, we know that minima and maxima are those points in which the derivative is 0. How we do this? So let's go to the theorem, to the proof of the theorem. The proof is technically can be done in a more general case, but I'm sure that you have heard about Rolle-Lagrange theorem for differentiable equations, but functions. But this is not so important. What I want to tell you is that Taylor expansion gives you this approximation. So here I am even assuming that the function has a second derivative. Okay? So we assume to have a function which can be approximated by a second order polynomial. The coefficients of the second order polynomial are given by the first and second derivative of the function in x0 plus a remainder. The remainder tends to 0 quicker than the second power of x minus x0. Okay? I'm sure you are familiar, everybody is familiar with this reasoning. Okay. Now assume that close to x0 as written here, close to x0, f of x is greater than f of x0. So this quantity is, when x is close to x0, is always positive. Okay? If you are, I repeat, the precise mathematician will believe that what I'm telling now is dirty, not precise, not rigorous, and it is not precise. It is neither precise nor rigorous. But I want to give you the line of thought which has driven Lagrange to a generalization of the criterion of zero derivative in a minimum to get a similar criterion for functionals. Okay? So, by analogy, we will try to deduce a similar condition with a similar reasoning which applies for functionals. Okay? I know it is rather difficult. I could tell you here the solution in terms of modern functional analysis, but this is not good. You must understand why a certain definition has been given. Okay? So, let us follow this reasoning in the simple case which you already know. Because it is impossible that you arrived here. Maybe you could be here without having understood it. But it is impossible that you could arrive here without having seen, written in a book or discussed by a professor, this kind of Taylor expansion. Okay? So, do you agree that this is always positive if we are in the neighborhood of a minimum? This is by definition, which I've written there. Okay? Then, if I go close enough, so if x is close enough to x0, then this remainder is not influencing the sign of the quantity. Okay? You remember the theorem of permanence of sign. If a limit is positive, then in the neighborhood, in a point, then in the neighborhood of that point, the function having a positive sign must be positive. Okay? So if I'm close enough to x0, this sign remains greater or equal to 0. Okay? Okay, I said the other implication, but you understood. Okay? If I have a positive function, the limit has to be positive. Okay? Good. Then, the sign of this is dictated by the sign of the second derivative, because this is positive. Okay? So I go close enough to x0 to be able to neglect also this quantity. Okay? This is possible. Look, can f prime of x0 be positive? No. Because if it were positive, x minus x0 negative would imply that this quantity is negative. And this is against our hypothesis. Can f prime of x0 be negative? No, because in that case, x minus x0 positive would contradict our assumption. Therefore, in a minimum, f prime of x0 must be 0. In other words, the linear approximation of the increment of the function f is given by the linear function 0. Okay? So, the linear approximation is trivially given by the 0 linear approximation. In a minimum, the same holds for a maximum. Okay? So, f prime x0 is 0. Then this term disappears, and this becomes the dominant term. So we have another information. In the neighborhood of a minimum, the increment of the function is quadratic. It goes to 0 very quickly. Okay? Not only the second derivative of f has to be positive. Okay? So we have a criterion for discovering minima. The linear approximation of the increment of the function is 0, and the quadratic approximation of the increment has to be definite positive. Okay? So, just for telling you this, when Lagrange started studying this problem, the problem of finding minima of a functional, this mathematics we are discussing now was not fully developed. And indeed, the fundamental theorem which allows us to make these reasonings is named after Lagrange. Okay? Do you remember, probably, I remind you this, if I have a function having the same values in A and B, the function is differentiable in the open set AP, and it is continuous in AP, then at least in one point you must have the derivative equal to 0. This theorem by Lagrange is essential for proving the validity of the Taylor expansion, which I gave you, and the criterion for maxima and minima. Okay? And this theorem has been proven by Lagrange. So, what I'm trying to teach you is exactly how Lagrange invented the concept of first variation of a functional following the reasoning of Lagrange. Okay? In this, I hope that I will manage to show you how a novel idea has been invented. The hope is that you can invent in future something like that, keeping in mind how it has been done in the past. Okay? Very well. So, which are the ingredients of the Taylor expansion formula for continuous differentiable, 2 times differentiable function. You must tell what it means that x is close to x0. Otherwise, all these reasonings are totally meaningless. So I must define what it means that one configuration of your beam is close to another configuration of this beam. So I have the set of, okay, for simplicity, let us limit ourselves to the situation in which the beam is only displaced with transverse displacement. So W is 0. And let us assume that the energy is this one. This is a very simple model. By the way, I think that 95% of buildings which surround us have been designed with this energy. Everybody who has followed a class of structural engineering will remain surprised by discovering that this is the energy used up to now for designing nearly everything, including the wings of the airplanes. The twin towers in those who collapsed in the famous 2001 attack. Okay? We will discuss why such a simple model can work. It's simple. Engineers are building what they can control. So they are building only beams whose energy can be this one. And they refrain from using other beams. Okay. Only recently they dare to try to do more complicated things. Okay? So, I have a function, and u1, I have another function, u2, and I want to understand what it means that the two functions are close. Okay? So we have a set of functions, and we want to introduce a metric inside this set of functions. We will discover that this is not a simple task. What it means? Let me be more precise. It means that we have many possibilities which are all logically reasonable. And we must invent a criterion for choosing among the many possibilities. This is the point. Lagrange invented a metric which is called Lagrange metric. So dl of u1, u2 is by definition, Lagrange assumes that u1 and u2 belong to C0. For an engineer, this request is clear. I want a beam, and this beam is not broken in the process of deformation. Okay? So, if you like, this is another meta theoretical assumption. We want to study elastic phenomena. What is an elastic phenomenon? You deform a beam, you give to it an energy, then the beam comes back to the old shape and it gives you back all the energy. Okay? I assume that you are familiar with the main ideas of thermodynamics. Okay? So an elastic phenomenon is a phenomenon in which you have conservation of energy. Now, even if we are dreaming about very strange meta beams, beams whose behavior is very exotic, I never heard up to now about a beam which you break and then you reconstruct, and in the reconstruction process you get back the energy. But it is wise not to say that this cannot be possible. Imagine to make a beam made of small magnetic balls. You find in internet some movies of a toy made of magnetic balls. You detach them, you need an energy. When you abandon them, they come back and they give back the energy. So one probably can invent this kind of things. What do we conclude? Don't be naive. We will not conclude that our assumption that the functions are continuous is wrong. We conclude that the model by Euler, Lagrange, is not applicable for those beams. We can apply our model only to beams which, in elastic phenomena, remain continuous. Okay? So it is another limiting assumption for the applicability of our model. Okay? You should accept that I will repeat this kind of considerations all the time. Because I must teach you that a mathematical model can be applied sometimes, cannot be applied other times, and there is no paradoxical behavior of reality. Because my fundamental ontological belief is that reality is logic. Okay? Maybe I already told you, I will repeat, because I'm becoming senile, so I don't remember exactly what I said to you first. Second, I have an excuse. I'm teaching in parallel another class for civil engineering, and some students here are also students there. So I don't remember what I said where. So you forgive me if I repeat something. Okay, I am senile, but not so much. Okay? I have some excuse. So, the big debate between Galileo and his Jesuits opponents. By the way, in the history of church, I know that you, all of you here, the great majority here, has not a Catholic tradition, probably, or another tradition. You must learn how sophisticated was the Catholic intelligentsia. You had Dominicans, which were the first intellectuals of Catholic Church, and then Jesuits. Dominicans became less well educated after the arrival of Jesuits. So to be honest, the first opponent of Galileo was not a Jesuit, he was Dominican. Okay, so there was a big debate, and these scholars claimed that Galileo could not conclude anything about reality. Why? Because God can change the law of physics. He is omnipotent. So one day he can decide that the interaction between Sun and Earth is not ruled by the law of 1 over r for the force, or 1 over r squared for the force and 1 over r for the energy. We can suspend the laws of physics. Why not? Okay? And the Pope said these words himself. Do you know why Galileo risked to be killed? Because he pulled the leg of the Pope in his book, telling, in the mouth of Simplicio, Simplicio means simple-minded man, okay? He placed in the mouth of Simplicio the statement about the possibility of having laws of physics which change in 1 second or another one. Okay. We don't believe this. What I want to tell you is that if you take 200 beams, all equal, you impose to them the same boundary conditions, all the 200, 2 millions, they form in the same way. If you are on the moon, if you are on Alpha Centauri planet, if you are here. Okay? So we believe that one model which works in given control situations is always applicable under those situations. Okay? So I will repeat this to you many times. It is very important that you, because if we don't tell you, one day somebody will say that God can change the laws of physics, completely forgetting a debate which lasted centuries. You know? Like for vaccination, as we don't have any disease because we are all vaccinated, therefore vaccination is useless. And there are people who claim that vaccination is useless. We must repeat every day that vaccination is useful, because otherwise 3 billion human beings were dead because of the diseases which we can fight with vaccination. By the way, do you hear any Novax now in the epoch of coronavirus? They stopped talking immediately. Now they want vaccination. Okay? Okay, let's go back to our problem. Now, which is the idea of Lagrange? Two beams are close if the displacement u1 and the displacement u2 have the maximum of u1 of s minus u2 of s belonging to 0L smaller than r. So this is the definition of distance by Lagrange. Okay? Now, we need to discuss the development of the theory for discovering that this metric is not good. And the reason for which this metric is not good is due to the engineering applications we have in mind for the theory of being. By the way, this I tell for the Italians present here. There is an old book of strength of material called Baldacci, which has been despised because it is too mathematical. Many engineers claim it is too difficult. The reasoning which I'm developing now, I have not found in any mathematical book. I found in the book of Baldacci, who was an engineer, full professor of Scienza delle Costruzioni in Genoa University. Okay? So, this proves that engineers can be clever mathematicians if they want to understand things. Okay, but let us go ahead. Okay. If you introduce this metric, you have that this function and this function are close. Okay, maybe it is worth that I repeat, if I already said to you, what is a ball centered in U1 having radius r. You have the function U1, then you consider the translation U1 plus r, U1 minus r, okay? Every function having its graph inside this stripe, by this definition, is inside the ball of center U1 and radius r. Okay? So, think about this energy, and you will discover immediately that this metric is not good. Why? Because you can have two shapes which are very close, however, the second derivative of this shape is low, the second derivative of this shape is very high, and these two integrals are different. Okay? So, look, I use US is the displacement for the beam, but when I want to underline the fact that a displacement is deforming a beam, I call it shape. Okay? In this moment, I want to underline that the beam is changing its shape because of the displacement US. Okay? Okay, but this situation can be solved rather easily, because instead of using this distance, so we can define the Lagrange matrix DKL U1 U2 if Ui belongs to CK, I equal 1 and 2, this distance can be max for S belonging to 0L of what? Absolute value of U1 minus U2 plus absolute value of U prime 1 minus U prime 2 plus UK 1 minus UK 2. Okay? So, I can define the distance between two beams imposing that the absolute value of the placement plus the difference of placements plus the absolute value of the difference of derivatives up to the order k, this maximum is small. So, these two I cannot draw. easily what is a ball in this metric. But these two functions are not closed because their first and second derivative are not closed. So this addend is closed, but this addend is not closed, and this other one is not closed. Okay? So at the end of the story, I can improve Lagrange metric, and improving Lagrange metric, I can control also the derivatives up to the kth order. Okay, I have a good news. The good news is that this space is complete. The metric space of CK with this metric is complete. Every Cauchy sequence is convergent. So we could be very happy. We would say, wonderful, we have done it. Okay, we take C2. We consider the metric D2 Lagrange. This energy is continuous. We can do everything. Okay? We can do something. But the bad news is that we cannot do everything which engineers need. So the next part of this lecture, plus the next lecture, will be dedicated to understanding why this metric is not good. Okay? Okay. Being optimistic and following Lagrange, we take this energy and we try to write the first variation of this energy. So what we try to do, we try to write the Taylor expansion of this energy. So what we do, we take E of U bar plus a small variation of U bar, we call it delta U, minus the energy of U bar. You remember, we wrote Fx minus Fx0. So there is a small change of notation. X I've called x0 plus delta x. Okay? I need to keep in my mind that I add to U bar something small. Okay? Therefore, you understand why all our discussions about metric spaces was needed. Because one could ask me what it means, small. Okay, so now I tell you, we have a metric space. The functions we are considering for this energy is a metric space. Delta U is a function which is close to zero, in the sense of my metric space. And here you can understand how Lagrange was very clever. He had in his mind the wrong metric. However, he did not build his theory for that metric only. He kept his reasonings general enough that we could change the metric. So this is the sign of being a genius. He never made a useless assumption. He could have done calculations in which the particular metric he has in mind was used. Instead, he made his reasonings vague enough to be ready to change the metric. Of course, he has been criticized for this. Many scholars claim that the reasoning I'm showing you is not rigorous enough. In reality, in the language of metric spaces, it can be made rigorous, changing the metric. Okay? So now we try to remain in a general setting. Okay? So we want to estimate this first variation. We have a finite variation, and then we want to find the first variation of this, neglecting higher order terms. Okay? So this is equal to integral between 0 and L of alpha over 2 u plus delta u second squared minus alpha over 2 u second squared. Okay, you are not surprised that the integral is a linear operator, so the difference of the integrals is equal to the integral of the difference. Okay? Now, I have chosen this particular operator because in this way we will do it more generally, and in the book there is a chapter where the more general derivation is presented, hopefully without errors, because in the first version we had some errors left. Okay. But you know, here I hope you are able to calculate the square of a binomial expression. Okay? So we have integral of alpha over 2, which can be factorized. Then you have u second squared plus 2 u second delta u second plus delta u second squared minus alpha over 2 u second squared. Okay?
I think of half is not there.
Yes, you're right. I don't know why I'm copying. Yes. Okay. Correct me all the time. I'm thinking next step and I'm copying blindly. Okay, so this goes away with that. Okay? This is the square of something small, and this is a linear function of something small. So delta u second is negligible. So the linear approximation of this variation is integral between 0 and L of alpha. This 2 simplifies with that 2 u second delta u second. Now you understand, I hope, why we needed to discuss carefully about metric spaces. If delta U is small, delta U second is small. You know, I arrived to elaborate this lecture in this way, especially because I had the experience of teaching to some clever students. So, systematically, for a long while, when I was teaching to electronic engineers, among engineers and electronic engineers are those who are more sensitive to mathematical precision, there was always somebody raising his finger and telling me delta U is small, but delta U second is not. So then I was obliged to tell him, wait, I am choosing the metric. So my metric is controlling the difference of the function, the difference of the first derivative of the function, and the difference of the second derivative of the function. Okay, so I am free to choose the metric which I need. By the way, Lagrange was not so stupid. In his book, he writes 10 pages for justifying why delta can be commuted with the second derivative. Because, look here, I have u plus delta u second. When I first read these 10 pages, I thought, okay, Lagrange was primitive and he did not know very well. You know, young people have the habit of considering that old people are all stupid. Okay? Of course, now I'm becoming old, so maybe I'm telling you this for this reason. But when I read Lagrange, I said, okay, this man was clever, but he did not know all mathematics, which I know because I studied mathematical analysis 2 centuries after, so he lost his time in discussing that, look, this is equal to u second plus delta u second, and then he said, delta commutes with second derivative. Think about it. The second derivative of something small is not small in general. Think about this example. If you go and read what Lagrange wrote, by the way, in a wonderful French, the mother language of Lagrange was Italian. Maybe you don't know that Lagrange was a clever man. He adapted to situations. His true name was Lagrangia. He moved to Berlin. French was very the language of science. So not only he started writing in French, but he also changed his family name, adapting to the situations. Okay? But you know, Lagrange was also very clever in other aspects. I will tell you other stories. Here I tell you that Lagrange was so clever that the king of France was the witness of his marriage. He married with a girl 30 years younger. The wife was agreeing with him when she understood that he was dying, who had to be the next husband. So he has chosen the husband he had to marry after he was dead. Oh, clever man. Revolution, that was a revolution. What do you think? A man who married having the king as witness, they killed him. You know what was French Revolution? They killed all noblemen immediately. Lagrange was belonging to a noble family in Turin. Lagrange was nominated president of the committee measuring the radius of the Earth. And he was considered one of the most influential scientists of the French Revolution. How he did it is not clear. Napoleon arrived. Napoleon nominated him senator. You know, so he was a follower of the king, a follower of the revolution, and he was faithful to Napoleon. He died, and he organized, before dying, he organized everything to be buried in the Pantheon. So he even organized how he had to be honored after his death. Okay? In a word, Jesuit education. Very clever. You must admire him. Typical Italian genius. Okay? He changed his family name, but he remained Italian in everything. Italian genius. You go and you read the French text describing the commutativity of delta with second derivative. You read it carefully and you discover that he says something like that. Choose the metric which you want. Whatever is your definition of being close, you need to choose a metric in which if two functions are close, their second derivatives are close. So you look at this and you say, this man was a genius. I told you quickly that delta you say. I did it easy, as you find in the great majority of books. This is the small variation of the value of u. This is the small variation of the second derivative of u. And as we can see, it is completely different in general. So, we have chosen one metric for which this change is possible. Okay? However, you don't like that metric for some reason, you change that metric. You can do it. But keep in mind that in your new metric, if one function is close to another function, the value of the function, the value of its first derivative, and the value of its second derivative, they must be close one to the other. Okay? And then the reasoning holds. Look how beautiful is this argument. Okay? Now we arrive in a point where Euler stopped. You know, Euler more or less did manage to make this, to arrive up to here, even if he had a debate about this delta commuting with derivatives. He was not sure about it. Okay? Now, Lagrange moved an important step. Integration by parts. If you have u second delta u prime I'm not carefully telling you if the delta and the prime, which is before the other, because they are commutative. Prime, what is this? This is equal to u third delta u prime plus u second delta u second. Now we are risking everything, because up to now our functions belonged to C2. And now we are calculating the third derivative of u. Lagrange writes, let us assume that we have more possible derivatives. We will see what happens. Okay? He's aware of what he's doing. You know, the poor Lagrange could not build Sobolev spaces. We will learn what is a Sobolev space. Okay, so let us assume that you can do this derivative. Therefore, this u second here, u second delta u second, can be written. Please copy another formula, otherwise I must do this way because the blackboard is not big enough. Okay? And please check my signs, because systematically I'm wrong with the signs. So u second delta u second is equal to u second delta u prime everything prime minus u third delta u prime. Okay? So I can write here integral between 0 and L of alpha bracket u second delta u prime prime minus u third delta u prime. Okay? Very well. This is the integral of a derivative. Okay? So I can write here alpha u second delta u prime estimated in 0 and L, because I have the derivative of this element integrated. Okay? So the integral of the derivative is the increment of the integrand at the end points of the interval. Okay? Calculus, first year. Okay? And then I have minus integral of u third delta u prime. Okay? I need to integrate by parts another time. So I have u third delta u prime. So what I do? This prime is equal to u fourth delta u plus u third delta u prime. Okay? So I can replace this animal with the minus sign. So let me write it here. I place minus, I place here equal. Okay? And what I do, I copy here the final result, trying to be right. So I start with this alpha u second delta u prime 0 L. Okay, and then let us do it slowly. Minus, so I place it, this minus here, plus here, minus here. Okay? So I have this plus so what I have integral between 0 and L. So here plus here minus inside here. Okay? So instead of minus u third delta u prime, I place u fourth delta u minus u third delta u prime. Okay? Somebody who knows about modern Poincaré inequalities, who knows about modern mathematics, discovers that Lagrange could walk like on a razor blade. He was walking on a razor blade in a very unstable equilibrium, and he found the right result without having all required mathematical theory. It is something unbelievable what he did. We go to the end, and I don't know if somebody among you ever heard about Poincaré inequalities. He will discover that here we are very wisely using, without knowing them, these inequalities. Okay. The integral of this derivative, so we have alpha u second delta u prime 0 L minus u third delta u 0 L plus integral between 0 and L of u fourth delta u. So I erase everything which is not needed. And what I conclude? This increment here, okay, this increment here can be linearized, and the linearized form is given by this expression.
How did the alpha disappear?
How?
The alpha, the constant alpha.
The alpha, you are right. The alpha is not disappearing. So here I have alpha, here I have alpha, and here I have alpha. It's not disappearing. Thanks. As I was very careful with signs, I missed the alpha. Okay? In our integration by parts, the alpha is considered constant, but you can easily incorporate it in the integration methods. But we make it easily with a constant alpha. Okay? In reality, if you are careful, if alpha is varying with x, with s, so if you have a bending stiffness which is changing with the parameter, this is alpha u second prime, and this is alpha u second everything second. Okay, this is obvious if you think how we did the integration methods. Okay? But what I want to underline now for you is, I have a small delta u. This delta u is varying the shape. Okay? I integrate between 0 and L alpha u fourth times delta u, and I get a part of the variation of this energy. But on the boundaries, if you vary delta u prime in 0 or in L, or if you vary delta u in 0 and in L, this energy is varying. The true essence of Poincare inequalities are in this relationship. You vary something on the boundary and you get a variation in some integral expressions. Okay? But I mean, this is very rough. I'm sure that a mathematician will be horrified by this statement I gave you. Okay? Okay, now we have a few minutes, so it is much better if I tell you what we will do next. Okay, so next time we must start from here. So please remember this deduction, and I think I know by heart this equation. I wrote it maybe 25 times in my life, at least during a lecture, but we need to start from this. Now what we have? We have that this equality, this variation has a first variation, this quantity, and we want that u is a minimum. Remembering what we said, minimum implies that this linear part is linear variation has to be 0. Okay? Because think about this expression. However you represent it, it is a linear functional applied to delta u. Okay? If this quantity is positive, you calculate it with minus delta u, and it becomes negative. So this difference cannot have a given sign. The reasoning is exactly the same. So if you assume ab absurdo that this L is not vanishing, you take one delta u for which it is positive. Then you change the sign to minus delta of u. L is linear, it changes sign. If L of delta u is negative, you calculate minus delta u and you get a positive quantity. So this L must be 0. So what we can tell? U is a configuration of stable equilibrium implies that for every delta u, this condition is verified. This is the celebrated Euler-Lagrange stationarity condition for this particular functional, but Lagrange wrote it more generally. Okay? Why Euler-Lagrange? Because Euler tried to find it. Lagrange actually found it. Euler was 40 years old, powerful full professor in Berlin. Lagrange was less than 20 years old. So Lagrange found very interesting to associate his name with Euler. In reality, this is Lagrange. Okay? What we need to do? To look which are the consequences of this equality. Okay? I think that we stop here. Let's hope we meet tomorrow.